Hello, guys. In this lecture, we're going to discuss a new topic, which is the conservation of energies. Or basically, what we will do is before we were saying that the work of a force on an object is going to be equal to the change in the kinetic energy of the object. And we were doing the work of any force, including gravity, right? So if you have an object, if you let go of the object, basically gravity will act on it, right? So the work of gravity is going to increase the kinetic energy of that system. If we have a friction, also friction will act in the opposite direction of the object, and then it will do negative work, and then the negative work will actually eat from the total kinetic energy of the system, and ultimately you will reduce the velocity. Turned out that for a few forces, basically, we can treat their work as essentially like energy. And what we will do is we're going to convert the work of gravity into an energy, and then we're going to call that the potential energy. All right. And in a similar manner, we're gonna also treat the work of springs as energy in the springs, and we're gonna take that as an energy level in a spring. So this is really the main topic here, and here basically we're looking at the spring here, right? If you, for example, if an object basically falls on the system, basically what happens is that we're going to say that if there is no friction or nothing, no other forces are applied on a system except gravity and a spring force, basically we'll treat that as simply energy, and we're going to say that the initial energy of the system is going to be equal to the final energy of the system, and we're going to use that to be able to solve various velocities and forces. There's one thing we are finding the energy. We're basically converting the work of the spring force and then the work of gravity, and then we're calling that a energy. And then the reason why we can do that is because both gravity and also the force of a spring are actually conservative forces. And by conservative forces, we mean that the actual total work of gravity will actually be independent. If you go anywhere and then if you come back to the same point, your total work is going to be zero, right? Why? Because you have no h elevation. So it doesn't really matter. So from A to B, let's say an object is actually going all the way around and it's coming back to A. The work from A back to A is actually zero. So this is what we mean by actually that circle. So the work around this closed path will actually be zero because the work of gravity is independent of the actual path, right? And same thing basically for spring, right? So if you compress the spring, decompress, etc., do whatever you want to do to it, and then come back to the same position, then your work is going to be zero, right? It's like the spring hasn't done any work, and that is why we say that the work of a spring is basically zero. All right. Mathematically speaking, when the force is only basically a function of position, right? Like in the case of the spring, it's kx, or it could be kx squared, it could be a nonlinear spring, or any force basically that is only a function of position. You know what I mean? Then that force is actually treated as a conservative force. Why is that? Because if you come back to the same position, then your force is going to be the same, right? So the work will always be zero if you do that. And how come the force of gravity, which is independent of position, in reality, it is kind of related to position, right? It's actually constant, right? So it doesn't even matter. It's not even a function of position. What really matters is that the force is not a function of the velocity, right? Or some other variables. Okay, whenever you have that force, then the work that the force will do will actually be conservative. Is that all clear? All right, so the total, we're going to have one potential energy in our case. So we're going to refer to the potential energy as V. So total energy is going to be equal to the gravitational energy, which is mgh basically, plus the work of springs. And the work of springs is going to be equal to 1 over 2 kx squared, where x in this case is the deflection of the spring. We're going to have many examples on that, and I think you guys will be able to clearly understand that. So, in actual, by definition, so what is the potential energy? It's a measure of the amount of work a conservative force will do when it changes position, right? So, and that could be based on whatever reference that you want to give, right? So any reference, you can choose the reference basically, and then you're going to increase the potential energy. But what really matters is that when you are solving these types of problems, you want to say the energy, the first energy at state 1 has to be equal to the second energy at state 2. So whatever references that you have will actually cancel out. So whatever datum that you choose will actually be eliminated. All right, so here, work of gravity will always be equal to mgh, but h is with respect to some datum. In this case, it's mg, which is w times y. So I'm gonna set up my datum, and I can set up my datum to be any position, right? It could be my initial position, my final position, or none of them. Basically, in this case, it could be the middle position, and if my movement start here, then my potential energy is. So let's say this is my datum, and the point went from point A at the bottom to point B on top. Then my initial potential energy is going to be equal to minus mgh. My final potential energy is going to be mgh. All right. If I set my datum to be 0 here at the bottom, then my initial potential energy would be 0, and the final potential energy is going to be 2. Right. So we have y and y. We have 2y. So mg multiplied by 2y. Nice and simple here, but potential energy of springs is going to be 1 over 2k times the deflection of the spring. Sorry. So S is the deflection of the spring measured from the freelance position, right? So you look at the equilibrium of the spring. So you have a spring on a table, right? It's not, you're not doing anything on it. The minute that you begin to compress it, so let's say it's fixed here. The minute that you basically begin to compress it, basically that distance here is going to give you your energy, right? Which is over 2kx squared. Okay, so we're going to do a few examples on that. So just be careful how we do that. Just remember that the potential energy of the spring at any state, right? You look at its length at that state minus the free length square, and the potential energy of the spring at state 2 is the length of the spring at that instant minus the free length. And we're going to be able to use these relationships to quickly actually solve the problems. And what I'll do is, so this is what we'll do. We say that the potential energy, or I'm sorry, the total energy of the system is not changing, so long as you don't have no non-conservative forces. Non-conservative forces are forces that depend on what? Friction, for example, right? Friction is a non-conservative force. Any type of a drag, for example, anytime where you are removing energy from the system or you are adding energy to the system, is basically your energy will not be conserved, right? So the total difference in the potential, in the total energy of the system. So I'm going to write it here. Okay, we can do this here. So my delta E, right? So the change in the energy of the system is equal to the summation of the work of all non-conservative forces. So you basically add all non-conservative forces. So the conservative forces, which are springs and gravity, will actually be here. So what is delta E? Delta E is the final energy minus the initial energy is going to be equal to summation of work of non-conservative forces. So the final energy of the system is equal to the initial energy of the system plus any work that you do. So sometimes you could actually be adding energy to the system, so your final energy will be greater than initial energy. Sometimes you could be removing energy from the system in the case where you have friction. So you will simply add it, right? So if I tell you that like a block was here, initially it had some velocity v0 at that state, A, and at state B, we had some friction that was applied on the block during that movement. How do I find the final velocity of this guy here? So I'm going to say the final energy here, E2, which is in this case, we don't have any potential energy, we have no springs. So let's say the velocity here is going to be V1. So what is the final energy of this block? Right? Well, what is energy? We said the energy at any state is going to be equal to 1 over 2, or is equal to, I'm sorry, potential energy plus kinetic energy. And we refer to potential energy as V, T as kinetic energy. So T is equal to 1 over 2 mv squared, and the potential energy is either mgh, which is pressure of any gravity, where h is measured for the datum, plus any springs that you have, k, l minus l0 squared, whatever springs that you have. In this case, we don't have any potential energy. So V, again, always potential energy, T is kinetic energy. So in this case, what is my E1? E1 is going to be equal to 1 over 2 mv1 squared. What is my V0 squared? Sorry. E1 is initial here, 1 over 2 V0 squared. What is E2? E2 is equal to 1 over 2 m V1 squared, right? So if I have no work applied on a system, then my final kinetic energy will equal to my initial kinetic energy. Then by comparison, V1 is going to be equal to V0. If I have some work done on it, then I'm going to simply subtract the work done, right? So what would that be? So 1 over 2 mv1 squared, my final energy, is equal to my initial energy. So if I have friction, what is the work of friction? So friction is acting like that. I know friction is going to be uk times mg. So minus uk mg multiplied by L, right? Whatever distance that it has traveled. So this is the work of friction. If I actually had a force that is pushing it at the same time, then what would be, what should I add here? I will just basically add the work of that force. What is the work of that force? P times L. So you just keep adding them on, right? So this is your final energy. If you had basically some, if this guy was kind of coming down, then you will simply add a potential energy, right? So what is the potential energy? Potential energy that we have to have a reference. And from that reference, basically, we can find the final kinetic energy. So this actually saves us a lot of hassle as we try to, before. This is called the indirect method, by the way. Anytime that you are calculating the velocity or some other parameters based on energy, it's called the indirect method. And if you are using Newton's second law, it's called the direct method. Basically, we do the summation of forces, we find the accelerations. We integrate the accelerations, we find the time, or somehow we compute the time. So from Newton's second law, obviously you find the acceleration and you find the velocity. You can find the position, right? Then you can find the time for that particle to reach that position. Once you find the time, you can come back to the acceleration, you can find the velocity from your velocity value. Right, so that would be the direct method, and then we've already done a lot on the direct method. Now we're going to see that with potential energies or with basically conservation of energy, we can actually solve many parameters in the system, like mainly the velocity, right? Velocity or displacement, because this is really what we are mainly interested in. All right, so by saying that the energy of the system will be conserved, we can actually solve a lot of things, and then we are able to quickly basically solve our problems. So let's look into this example 9. What we have is we have this 5 kilogram collar, and this is a collar which has a velocity of 5 meters per second along the guide at A. So basically at A, we have a velocity of 5 meters per second, right? And then at A, it's along this guy, so it's the velocity is horizontal. And by the way, when you're using the energies, the velocity direction doesn't matter, right? Because we're looking at the absolute value of the velocity. We need to find the speed of this block at B, right? And then when we find that at B, we need to find also the normal force. Like, when this guy is at B, what is the normal force? The spring has an unstretched length of 100 millimeter, and B is located just at the end of the curved position. So this is point B. So, all right, so we need to find that. We solve that. So let me open up my video again, and let me redraw this. So basically we have this guy, it's like that. This is A, and this is B. And this is my spring right here. And what we do know is that, this distance from here is 0.2 meter, which is 200 millimeters. And I know this guy is a radius, is a part of a circle. So this radius right here is how much? Is 0.2 meter as well. And so this is my spring. So the stiffness of the spring is given as 50 Newton per meter. All right, guys, so you see what is happening, right? So this guy, initially, the block is moving at A with PA equal to 5 meters per second. And we're trying to find the normal force at B. So how do we do that? Well, to find the normal force at B, we have to do a free body diagram, right? On B, how would the free body diagram look like? Well, this is a block, right? The spring is going to be here, so the spring is definitely stretched. So this is going to be the force of the spring, which is equal to K, the length of the spring at B minus the length of the spring at the free length, right? So this is the force of the spring at B. I think you guys should agree. We already know the length of the spring at B. We know it's free length. And, we have some weight on it, right? Also, we're not going to be using that weight. On the acceleration diagram, what do we have? We have this mv squared, right? mv squared, the velocity squared at B over R. And I think we're going to have some AT, right? Because we have mg, so we have to have mt. We don't need those, right? We're not looking into those. We're only looking to find well, we still have one more force, right? You have a normal force, right? So this guy is applying force like that, and maybe it's like this, but we're gonna assume it. We don't know. We solve for n. If it's negative, then it's opposite direction. If it's positive, it's in that direction. Okay, so ultimately, we sum the forces to the right. We're gonna say that n minus k lb minus l0 is gonna be equal to minus mvp squared over r. So the normal force that this guy would apply, right? So this is the force that the channel applies on the collar, right? So this is the reaction force in between. K lb minus l0 minus mvp squared over r. And then you notice that this is basically the centrifugal acceleration. Yes. Okay. So the more the velocity, you reduce n, right? Which makes sense, right? So this centrifugal acceleration is basically compensating against the spring that is actually present here. So I want to stop this so you can see the whole screen. And okay, so now we have the normal force. We need to find the velocity. We know the rest of these values. We just need to find the velocity at B. How do I find the velocity at B? Well, what I'll do is we'll simply say that the energy at A has to equal the energy at B. Do we have any other forces applied on the system, like friction or normal forces? We don't, right? Why? Because the normal force is always perpendicular to the motion, right? So it doesn't do any work. So here what we'll do is we're going to say, I'm going to just move it a bit. I want to say EA is equal to EB, right? So we need to have, what is EA? EA is the initial energy at A, so 1 over 2m VA squared, right? Plus, do you have any potential energy? We do, right? So I'm going to set up my datum to be here. I can say here that my, call it datum. Okay, so this is my datum right here. So energy at A, so I'm starting by writing energy 1 over the MVA squared plus mgh, right? So plus mg multiplied by h. What is h? H is 0.2. So I'm starting here. mg times 0.2. Any other energies? I think we have the energy of the spring, right? So at state A, the spring is going to be here, right? So plus 1 over 2 k. We said the energy of the spring is going to be equal to the current length minus L0, right? So what is the current length of the spring? Is going to be equal to that distance right here. Well, what is that distance? Well, we have 0.2 and then 0.2, right? So this guy here is 0.2 and then this guy is 0.2. So it's going to be this distance right here, the diagonal distance is going to be equal to 0.2 times square root of 2, right? So 0.2 multiplied by square root of 2, right here. So this is LF minus L0. What is L0? The free length of the spring is given to me by 0.1 100 millimeter or 0.1 meter. Okay, so this is the energy of the spring at state A, right? So this is basically A, and this guy has to be equal to the energy at B, right? So what is the potential energy at B? It's going to be equal to 1 over 2 mvv squared. What is the potential energy? It's 0, right? Why? Because I'm at the datum. So point B is at the datum, so it has no energy. And by the way, the datum could be anywhere. Plus the final potential energy on spring, which is 1 over 2k multiplied by what? So if you look at the figure, and obviously I'm expecting you guys to have this open while you are watching the videos. 1 over 2k, the length of the spring at B, which is how much? 0.4, right? 0.4 minus 0.2 squared. So we forgot the square, guys. Some of you probably have caught it already. So 2k squared plus, so we have the velocity, right? Kinetic energy plus the potential energy plus what is the potential energy due to, gravity is 0. Okay, so we're good. So we need to find the velocity at B squared. So it might be a good idea to multiply everything by 2. And then I'm going to put it here. And so we can also divide by m. Divide by m. So k will be over m. K will be over m. So I think we're going to end up with a single line that VA squared plus 2 mg multiplied by 0.2 plus k over m, 0.2 square root of 2 minus 0.1 squared is equal to VV squared plus k over m 0.4 minus 0.2 square. So from here, basically, we can directly find VA square, right? So we know mg, we know k, we know m, we know all these values. We can find VA. I'll let you guys do this analysis. Oops, wait, we need to find VB, right? So we know VA. They gave you VA, you need to find VB. So it's very easy, right? So we already have VB here. So we'll just subtract these guys here. And then when you want to find n, just plug it into this equation, right? Which I already did before. Okay, so we use basically the conservation of potential energy to find the velocity or the final velocity. And from here, basically, what we'll do is we're gonna we use free body diagrams, etc., to be able to find the normal force. One thing that I want to mention to you guys. So let's say you have this equation and then you're trying to solve for VB. So in reality, VB squared is equal to what? So I'm gonna basically bring these over here. So I have 2mg multiplied by 0.2 plus k over m minus 0.1 squared minus k over m all right. So we have VB squared. What happens, you're on the exam, you're trying to get some, you're trying to get some stuff done, trying to get a good grade on the second midterm, you solve this, right? And then ultimately you actually have a negative number here, right? So you're trying to find the velocity at B, but the value here is negative and you have a square root, so you have a problem. One workaround would be to actually add a complex number and then you just put an I here, right? Multiplied by I squared, just like an imaginary number, right? But what does it mean? It means nothing, right? What that actually means, whenever you are using potential energies or conservation of energies and your velocity here would be negative, what that simply means is that you will not be able to actually reach that position, right? And I'll actually be able to give you a small problem, because when we use the conservation of energy, it's like you assume that this motion has occurred, and now what is the velocity, right? So if I told you that I threw a ball, right, with some velocity v0, and find me the velocity of this ball after distance h, right? So it was at A. Find me the velocity of this ball at B, and I'm gonna call that v1. How do you find v1? You tell me, okay, I'm gonna use conservation of energy. I'm gonna set this guy to my datum. I know EA has to be equal to EB because I don't have any rocket connected to this guy. So EA is equal to EB. What is EA? Is equal to 1 over 2 m VA squared. And that's it. It has no potential energy. So kinetic potential energy is here. At B, what is my kinetic energy? 1 over 2 mvb squared plus whatever potential energy that I have, right? So the potential energy is actually eating from the initial energy, right? So plus mgh. Okay, now you try to find VB squared. You're gonna basically, depending on, so if you multiply all these by, so take m out, multiply by 2. So it will be equal to VA squared minus 2GH, right? If VA squared minus 2GH, so if you increase H a lot, obviously it will not be able to reach it, right? So what I want to tell you guys is whenever you are using the conservation of energy, you really, implicitly mean that the motion has already occurred, and now let me find the velocity to see what is remaining. If there's any energy remaining in the system, that energy has to be velocity, right? But if there's no energy remaining in the system, then your motion has already ended, right? A bit before your assumption. So just something to keep in mind. Let's do a few more examples, and we're actually done with this. So now we can start with other more interesting stuff. Okay, so another problem here is example 10. And what I have here is that the 0.75 kilogram bob, which is a weight pendulum, is fired from rest at position A by a spring which has a stiffness of 6 kilonewton per meter. So I know the stiffness of the spring, and it's compressed 125 millimeters. We need to find the speed of the bob and the tension in the rod at points B and then C, right? And they tell us that where the radius of curvature is still 0.6. So basically, it's going along a pure circle. How do you find the velocity at B? Right? How would you find the velocity at B? So what we'll do is we're going to simply say, and now I want you guys to be looking at A because I think my screen is basically cropped, so you need to actually have your your document wants to be able to see that. So I want to say EA is equal to EB, right? Because I don't have any drag applied on it. So this is my system, and it's doing this. Now I need to set up a datum. Let's say we set up data to be here, and we can say that V of gravity equal to 0 here. This is another way that you could do that, right? So is it write datum or say, V of gravity is actually potential of gravity is equal to 0. So I know that distance here is equal to how much? To 0.6. So the energy at A is equal to how much? So we have a spring that is connected, right? So we need to see what is the energy in the spring. So 1 over 2 K, it's compressed by how much? By 125 millimeters. So 0.125 squared. Never forget the square. Plus, what is the potential energy of that? It's minus, right? Because you are below that, right? So minus mg multiplied by 0.6 is equal to the kinetic energy here. What is the kinetic energy here? Or absolute total energy here is equal to 1 over 2. So it starts from rest. So initial kinetic energy is 0. So here at that point, we may have some velocity, so we're going to test. 1 over 2 m velocity at b squared plus the potential energy, and whatever potential energy we have here is going to be 0. Why? Because we are at the datum. So we can use this relationship to find VB, right? So we can multiply by 2. So this guy will vanish. This guy will vanish. And we can divide by m. Okay, so let me rewrite that. So I have k over m 0.125 squared minus 2g multiplied by 0.6 is equal to VB squared. So VB is equal to how much? Square root of k over m. I'll let you guys crunch in the numbers when k is given to you as 6 kilonewtons. So make sure you actually do 6 times 10 to the 3. All right. So k is not in Newton meter, it is in kilonewton. All right. So some of you on the exam will make a mistake. If your VB is negative, check the stiffness to make sure that you are not using the stiffness in Newton per meter. All right. Now, if I want to find the tension in the cord, how do I find the tension in the cord? You do A. So now you have the velocity. You can do a free body diagram. What would the free body diagram look like? So we have a weight. We have this mg. And then I have a tension. And that's it. And then here on my acceleration diagram, do I have an acceleration like that? Yes, because I actually have a force. So I must have some AT like that. And then on this end, we're going to have the mv squared over r. Well, we do have, and then this mv is mvb squared over r. So if you sum the forces in the right direction, then you're going to get T is going to be equal to m vb squared over r. Okay, so this is my tension. Now, if I want to find it at C, how do I find it at C? Then you're going to do the same thing. And we're going to say, we can easily use energy at A, if you already calculated this number, and then this would be the energy at A. Or we can rewrite that, or we can say the energy at B, because energy here is conserved. So I can say EA is equal to my final energy, right, at C. My potential energy at C is going to be equal to mg multiplied by h, in this case is 1.2. So it's positive plus whatever velocity we have, 1 over 2 m vc squared. So there's one thing I want to let you know, guys, that at point C, right, at point C, it doesn't really matter how the velocity, doesn't even need to be a pure circle, right? Because the energy, the kinetic energy is a function of the actual velocity. It doesn't really tell you how the direction of the velocity. So here we're just saying that, this energy has to be converted into two things, right? So if you have this elevation, then you know this is the work, this is the amount of energy that was taken from the initial energy as a result of just by merely of, overcoming gravity to reach that point. Plus, we're going to add the kinetic energy, which is 1 over 2 mvc squared, right? So, so this velocity here we don't know its direction. Maybe it's not actually doing a pure circle, so the velocity here would be kind of like this, right? Or it could be still going up. So we don't know that. So we need to basically find VC. And then if we want to know if this was actually in a full circle, how do we know? We find the tension. anaerobic. If the tension is positive, it means that, so basically from this we can find VC. It's pretty easy math, right? So we can find VC. Now we do a free body diagram. How does the free body diagram look like? So we have mg, and then we may or may not have a tension, right? So we're gonna do that is equal to, what do we have here? M V square VC squared over the radius, which is 1.2. So if I do this, I already know the VC squared. If I sum the forces in a vertical direction and then I try to solve for the tension, so T minus, I'm going to put T, T is downward. So minus T minus mg is equal to, let me actually write that. Okay, let's just quickly, rewrite that here. So when the ball is on top at C, we have the free body diagram here. We know mg has to be downward. If there is tension in the cable, it would be T. And then what else do I have here? Here, what do I have? I have simply M. VC squared over the radius. Okay, well, we want to see now if this is actually valid, right? So you can actually write that only if the movement is on a pure circle, right? If this guy was on a perfect circle, then we can actually say that, and then this would be our radius of curvature. So basically what we need to do is we need to sum the forces in the bottom direction, and then we can do T plus mg has to be equal to MVC squared over R. So we're going to assume that you are still maintaining a pure circle, and then we find what T is. So T has to be equal to MVC squared over R minus mg. Right? So we assume that the ball is basically on a pure circle. Right? So if the ball is on a pure circle, basically there is tension in the rope that is actually holding it. If that tension is positive, then my assumption is good, then I will just stop here. But if this guy was negative, what would that mean? This means that the ball is no longer on a pure circle. It means that the ball is somewhere here, right? And in that case, how would you calculate T? We'll have to do a new free body diagram. And then in this case, we don't have any tension anymore. We'll simply have what? We actually have AT. And right, because there's no more tension, so the ball now is free falling. It only actually has a tension like that in terms of acceleration. It may still have a velocity, exactly the velocity that we did calculate earlier, right? From here, we calculated the velocity at C based on the kinetic energy, but this velocity is not actually along a pure circle. It's somewhere here. It basically has some velocity like that, right? But it doesn't actually straight line, obviously. Right? It doesn't actually, it's not curving. So mg is equal to AT, and then we can actually solve AT like that. All right. One very last example, basically, we have a cylinder which has a mass of 20 kilogram and is released from rest when h is equal to 0. We need to find the speed when h is equal to 3. So each spring has difference of 40 kilonewton, and the unstretched length of the spring is 2 meters. Okay. Let me redraw that here. Okay, so you guys can see basically whenever that you are using the conservation of energy, the problem actually becomes much simpler and then easy to deal with. So we have basically some weight here. All right, and then we let go of the weight. It's gonna, the springs are gonna, kind of come somewhere here, and then this guy's gonna come somewhere here, and then here basically we have distance of h. So we're trying to find the velocity of this guy at h. Okay. Again, here, we assume that it actually went by h, and then let's try to actually find it. So we have two states. I'm gonna call it state A and then state B, and we're gonna set some datum here. I'm gonna set datum. This is my datum, and I want to say that energy is conserved. EA is equal to EB. What is EA? Is only what is it? EA is equal to the energy in the springs, right? Because potential energy is 0. My kinetic energy is 0. Kinetic energy is 0 because this guy was released from rest. And what else? Then you have your potential energy, right? Well, what is the potential energy? Well, the free length of the spring is 2. So even on top, the current distance is 2. So basically, we don't even have any energies at A. So the only energy that we'll have is actually at the bottom. What would be that? So we have a potential energy, which is minus or positive minus, because my datum is here, right? So minus mgh, so this is my mgh, plus the kinetic energy of the block at B, so plus 1 over 2 mvb squared, plus potential energy of two springs. So 1 over 2 times 2k, right? So it will be simply k. L, the length of the spring here, L minus L0 squared. Okay, we know L0 is equal to how much? 0.2. What is L? So we need to find L at that distance. What is L? Is basically Pythagorean, right? So square root of 2 squared plus h squared. All right, so from we know M, we know G, we know H, we know this guy, we know K, we can find V. I'll let you guys, have fun with it and then do the math. So that really sums up this chapter. I want you guys to solve these problems on your own, and I'm looking to actually have a live session. Sometimes this week. I'll let you know exactly the details. Please make sure to solve all the assignments. Make sure you stay up to date with the course. And any questions, just please feel free to email me. I'd be extremely happy to set up a Zoom call to actually discuss your concerns.